In this module, we'll take X.509 certificates from mysterious blobs to something you can actually read and design. You'll see what each field and extension does, how clients interpret them, and how to analyze real certificates using practical tools. Public key cryptography gives us powerful math, but on its own, it doesn't say who we're talking to. PKI solves that by binding an identity to a key. A certificate asserts that a specific person, device, or service controls a particular public key, and a trusted certificate authority signs that assertion to vouch for it. An X.509 certificate is really three logical layers working together. At the top is the to-be-signed certificate, identity data, validity period, and key material. In the middle is the signature algorithm, like RSA with X.509, which defines how the signing is done. At the bottom is the signature value, the cryptographic proof. Clients verify trust by recomputing the top layer through the specified algorithm and comparing the result to that signature. At the base of every X.509 certificate are a few identity fields that everything else depends on. The version tells clients we're using v3, so extensions are allowed. The serial number uniquely identifies this certificate, and CRLs and OCSP responses use it when revoking. The issuer field names the CA that signed it. The subject field names the entity the certificate represents. Together, issuer plus serial number and the subject form the core identity. Certificates live in a very specific window of time. The notBefore and notAfter fields define when a certificate is supposed to be trusted. If a system clock is off, you get clock skew. Valid certs can look expired or not yet valid. Within that time window, the embedded public key defines how trust works. Which algorithm, what key size, and any parameters. Time decides when it can be used. Cryptography decides how strong that use is. Basic constraints is the X.509 safety rail that stops your hierarchy from accidentally growing new certificate authorities. A certificate with CA equals true is allowed to issue more certificates. Path length then limits how many CA levels can exist beneath it. Leaf certificates are explicitly marked CA equals false. That tells clients, trust this certificate only as an end entity, never as a CA, and never to create new branches of trust. Key usage and extended key usage define what a certificate's key is allowed to do. Key usage is low level. Can this key sign data, encrypt session keys, or sign other certificates? Extended key usage is higher level and maps to scenarios: TLS server, TLS client, code signing, email protection, and so on. Tightly scoped usages limit the blast radius when a key is misissued or compromised. For modern identity and certificates, set aside the old common name field. Contemporary TLS clients validate host names strictly against the subject alternative name extension. The SAN can hold multiple identifiers, DNS names, IP addresses, and even custom name types. The CN might still be populated for legacy reasons, but browsers and libraries generally ignore it for hostname checks. So in any new PKI design, policy, or automation, treat the SAN as the single source of truth for identity. Enterprise identity binding is about making certificates line up exactly with accounts in your directory. In most Windows environments, that means using the UPN in the certificate's SAN to point at a single AD user object. When that mapping is stable and unique, you can support things like smart card logon and Kerberos authentication without extra directories or mapping rules. If UPNs don't match reality, logons fail or the wrong account ends up associated with the certificate. When a client validates a certificate, it walks through a series of checks. First, it builds a complete chain up to a trusted root. Then it verifies time validity, not before and not after. Next, it cryptographically verifies each signature. It then checks revocation status. After that, it enforces constraints and key usages. Finally, it matches the requested identity to the certificate's SAN. Any failure along the way stops trust immediately. Under the hood, that validation is really about a path of signatures. The root CA is trusted a priori via the operating system or browser trust store. An intermediate CA certificate is marked as a CA and is signed by the root, so it inherits trust but with constraints. The end entity certificate is not a CA and is signed by the intermediate. If every link verifies and policies align, the whole chain is accepted. When you inspect a certificate with OpenSSL, don't stop at the subject and issuer. 3 extensions quickly tell you how it's meant to be used. Basic constraints answers. Is this a CA certificate or just an end entity? If CA is true and path length is set, this cert can issue others. Extended key usage narrows the allowed purposes, like TLS server auth or client auth. Subject alternative name lists the actual identities, DNS names, IP addresses, and sometimes user principals. Looking at a certificate in a browser or in Windows CertMyCR shows the same X.509 data just rendered differently. As an engineer, focus on how reliably each tool surfaces critical extensions. Subject alternative name must list every hostname or IP the service will use. If it's missing, clients can reject the connection. Basic constraints tells you whether this certificate can issue other certificates or is just an end entity. Misreading either can lead to subtle, painful trust issues. Think of the 3 certificate types as different risk tiers. Roots are the most powerful, so they're tightly constrained, live for decades, and must stay offline in HSMs. Intermediates still have CA power, but with less scope, shorter lifetimes, and online HSM protection. End entity certificates have no CA privilege, very short lifetimes, and often just software or TPM key storage. Good PKI design keeps power near the top and exposure near the bottom. When you debug or design certificates, use this mental checklist. First, confirm identity and scope. SANs match the service, and validity dates are appropriate. Next, confirm the chain, issuer DN, path length, and CA flags. Finally, enforce security controls, correct key usage and EKUs, and strong signature algorithms.